Ever wanted to be a chemical detective? Well, today we're going to do just that. We're diving into one of the most powerful tools in a scientist's toolkit for finding that one hidden substance in a super complex world. It's a technique called gas chromatography mass spectrometry, or as we'll call it, GCMS.
So, let me ask you this. How would you even begin to solve a case like this? I mean, seriously. Imagine you have to find one single drop of some illegal drug mixed into an entire Olympic-sized swimming pool. It sounds completely impossible, right? Well, this is exactly the kind of challenge that scientists deal with all the time.
And this really is the classic detective problem, finding that proverbial needle in a haystack. The whole issue is that pretty much everything around us is, well, it's a giant, complex chemical soup. Just think about it for a second. The air you're breathing, a sample of river water, your morning coffee. None of these are just one thing. Nope. They're crazy, complex mixtures, often with hundreds, sometimes even thousands, of different compounds all jumbled together. So the real trick isn't just looking for something. It's finding and identifying one specific molecule in that massive chemical crowd.
Okay, so to solve this, we need a solid two-part strategy. Part one is all about separation. We've got to take that jumbled-up chemical crowd and get every single suspect to line up one by one. And the tool for that job is called gas chromatography.
At its heart, gas chromatography, or GC, is basically a sorting machine. Its entire job is to take a messy, complex mixture and just neatly separate it out into all of its individual parts. This is the first absolutely critical step in finding our needle in the haystack.
And the way it works is actually pretty simple. First, a tiny drop of the sample gets injected into the machine. Right away, it's hit with a blast of heat that vaporizes the whole thing, turning it into a gas. Then, that gas gets pushed by a carrier gas, usually something like helium, through this super long, super thin, coiled tube called a column. And it's inside this column that's where the magic really happens. The best way to think about it is like a racetrack for molecules. As all these different gas molecules travel through the column, they interact with a special coating on the inside wall. Now the lighter molecules, the ones with lower boiling points that don't really interact much with the coating, they just zip right through and finish the race first. But the heavier molecules, or the ones that stick to the coating more, they get held back and finish the race much later. And just like that, a messy mixture gets turned into a perfectly orderly parade of individual compounds. Okay, so the GC has done its job beautifully. Our chemical suspects are all lined up, single file, coming out of that column one after another. Awesome. But this only solves half the problem. We know something is there, but we still have absolutely no idea what each of those things is. We have a lineup, but now we need to make an ID. And to identify these suspects, we bring in the second member of our detective duo, mass spectrometry, or MS for short. This is our identification specialist. You see, mass spectrometry has one job, and it is brilliant at it. It identifies molecules. As each separated compound leaves that GC column, it flies straight into the MS. You can think of the MS as a kind of hyper-precise scale for molecules, one that measures something called the mass-to-charge ratio. So how does it do that? Well, inside the mass spectrometer, the molecules get blasted by a beam of high-energy electrons. This impact is so intense that it not only knocks an electron off the molecule, giving it a charge, but it actually shatters the molecule into a bunch of smaller, charged pieces. Now here's the crucial part. Any specific type of molecule, it will always break apart in the exact same way, creating a unique and predictable pattern of fragments. And this pattern, well, it's basically a molecular fingerprint. Just like your fingerprint is unique to you, a mass spectrum is unique to a specific chemical compound. All we have to do is match that fingerprint to a giant digital library of known fingerprints, and boom, we've got a positive ID. So now, let's bring it all together. When you physically connect the separating power of gas chromatography directly to the identifying power of mass spectrometry, you get GCMS. It is the absolute ultimate chemical detective duo. It's truly a perfect partnership, isn't it? The GC handles the messy part, taking that complex sample and feeding a nice, clean stream of individual compounds into the MS. And the MS, in turn, takes each one of those compounds as it comes out and instantly tells you what it is based on its fingerprint. Separate, then identify. It's that simple. And this is exactly why GCMS is called the gold standard in so many different fields. See, if you just used a GC with a simpler detector, you'd get a chart with a bunch of peaks. You'd know something came out at, say, the 5-minute mark, but you'd have no clue what it was. It's a dead end. But with GCMS, that same peak gets analyzed by the mass spec, it gives you the fingerprint, and you get a confident, positive identification. It's a total game changer.
And that incredible combination of abilities, separating complex stuff, identifying unknowns, and even measuring how much of something is there, makes GCMS just an essential tool. It's used everywhere. We're talking forensic science, environmental testing for pollutants, checking our food and drinks for safety, and even in developing new life-saving drugs.
All right, we've got the big picture. But let's get a little geeky for a second and peek under the hood. How does the mass spectrometer actually sort all those molecular fragments to build that fingerprint? Well, it uses a part called a mass analyzer.
The most common kind you'll find in a GCMS is a quadrupole mass analyzer. Now that sounds complicated, but just think of it as a highly selective mass filter. It uses 4 metal rods and some clever electric fields to create a path where only ions of one specific mass can make it through to the detector. Everything else, it gets kicked out. It's like a bouncer at a club, but for molecules.
And what's really cool is that you can use this mass filter in 2 main ways. First, there's scan mode. This is like using a big, wide-beam flashlight in a dark room. The instrument scans across a huge range of masses, trying to see absolutely everything that's in your sample. It's perfect for identifying a total unknown. But what if you already know what you're looking for? Then you use SIM mode, which stands for Selected Ion Monitoring. This is like swapping your flashlight for a laser pointer. You tell the instrument, hey, only look for these 3 specific masses that I know belong to my target. By focusing like that, it becomes incredibly sensitive and precise, which is exactly how you find that single drop in a swimming pool.
So, if you take away just one thing today, let it be this. GCMS is a beautiful 2-step detective process. It perfectly combines the power to first separate a chaotic chemical crowd and then to positively identify each and every individual in the lineup. It takes a seemingly impossible problem and makes it routine.
And this technology is only getting better, more powerful, letting us see our world in ways we never could before, down to the parts per billion or even parts per trillion level. It really makes you wonder, doesn't it? What invisible threats or what hidden wonders in our world are just waiting to be revealed by the next generation of these amazing chemical detectives?